Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're looking at an equation. What is the equation? The im, which is the imaginary part of z squared equals 4. Z is a complex number, needless to say, I think, and we're trying to find the set of complex numbers for which this equation is true. In other words, this could be considered a locus problem. We're only given one equation. Now let's think about some generalizations first. First of all, I want to find out, do you think the imaginary part of z squared is the same thing as the imaginary part of z squared? I want you to think about it first, and we can definitely take a look at the proof, right? Because we know that with absolute value, for example, the absolute value of z squared is the same thing as absolute value of z squared. And you can easily prove this, right? Think about it. Replace z with a plus bi, so on and so forth. So we have this nice property, which is actually very helpful. And another good thing about absolute values is that the absolute value of z is the absolute value of z bar. They are also equal. This allows us to solve a lot of good equations. And we've done those problems before, so I'm going to refer you to those previous videos. But with this one, do you think this identity is true, or is this an identity? How do we find out? First of all, we're going to go ahead and replace z with a plus bi and evaluate both expressions. What is z squared if z is equal to a plus bi? Well, you're just going to square this, right? A squared plus b squared I squared plus 2abi. I squared is -1. Hopefully you didn't forget that, right? And that gives us z squared equals a squared minus b squared plus 2abi. So it kind of helped to write the squares first because the real parts and imaginary parts are already separated. So this is z squared, and what am I going to look at? The imaginary part of z squared, which is 2ab. Okay, let's save that for now and look at the right hand side. What is the imaginary part of z? And then we have to square it, right? That's what we gotta find out. First, we gotta look at what z is. Z is a plus bi, so the imaginary part of z is b, and the imaginary part of z squared is b squared. So we found two things, 2ab and b squared. Are they the same thing? Are they identical for all values of a and b? Are they always equal? The answer is no. You can definitely find counterexamples. It's very straightforward. So this is not a general identity. It's not true in general. But could there be some cases for which this is true? Absolutely. And we could probably do another video on that one. But yes, you can do it and you'll find some answers. And if this were true, why did I look for something like this? Because if this were true, then I would conclude that the imaginary part of z is either 2 or -2, and the solution would be probably easier. I don't know. Anyways, we don't have that identity, too bad, so we have to go with something else. What is our method? The standard method. Replace z with a plus bi, but don't worry about any identities. So if z is a plus bi, then z squared again is a squared minus b squared plus 2abi. You might want to memorize this. This is very helpful. And then not too hard, right? Hopefully. And then I'm going to look at the imaginary part, which is 2ab. Wait a minute. It was that simple? Yeah. Just square it. Look at the, make sure you do it correctly. Everybody makes mistakes, right? Including me. Of course, I do make a lot of mistakes. But anyways, 2ab. And we're supposed to set it equal to 4. Oh, great. So I got the solution. But what does that mean? This means ab is equal to 2. Again, what does that mean? It just means that you have a complex number, z equals a plus bi, and you can replace b with 2 over a, and then you can write z as a plus 2 over ai. So whatever a is, of course, a can't be 0. No. But anything else is fine. Then we're going to find infinitely many complex numbers. Interesting. So this is a locus problem, and we're getting infinitely many solutions. But what kind of structure do they have? So let's go ahead and go from the A plus BI world to the X plus YI world. And the reason why I insist on A plus BI is because the name of this channel is A plus BI, right? Hopefully you know that. But wait a minute, why didn't I pick X plus YI for the channel name? Because A plus BI I like better than X plus YI, but sometimes I have to use that. Anyways, so we're gonna do the following then. We got AB equals 2, and we're gonna go from A plus BI to X plus YI. So A is gonna be replaced with X and B will be replaced with Y, and here's my equation. Now, obviously, locus problems or locus equations better be expressed with X and Y, because we're gonna go to the Argand plane, which is a fancy name for the coordinate plane, where the x-axis, the horizontal one, is called the real axis, and the vertical one is called the imaginary axis. So this one, if you put an RE here and IM, you are on the Argand plane. Okay, but that's no different from the coordinate plane, and every complex number is expressed as a point, or you can connect it to the origin since it has a direction and a magnitude. You can also express it as a vector. Okay, too much lecturing. Let's get to work. What does this mean? It means that when I have a complex number like X plus YI, its real and imaginary parts satisfy this type of equation, right? So pick any two values like X and Y values such that their product is 2. For example, Z can be 2 plus I, Z can be 1 plus 2I, Z can be 1/2 plus 4I, 1/2 minus 4I. Wait, that doesn't work. But if I pick a negative 1/2 minus 4I, yes, they're all going to work. So here's the $1,000,000 question. If I graph these on the Argand plane, what kind of shape would I be getting from this locus or loci, whatever? Locus, locuses, loci. 2 plus I, let's see if we can kind of scale it appropriately. I'm going to use 1/2, so let's make the 2 a little bigger. So suppose this is our 2, and then I'm going to break it down like this. So 1/2 plus 4I, I'm probably going to need a little bit more here. Let's make our taller, right? And here, this is going to be like 4. This is going to be my 2. This is 1/2. This is 1. And this is 2. Okay? So 2 plus I. 2 plus 1I is going to be here. 1 plus 2I is going to be like here. And then 1/2 plus 4I is going to be up here. And then negative 1/2 plus negative 4I is going to be just on the other side. So there's a symmetry. And then if I connect these dots, and obviously if I look at Z equals 4 plus 1/2 I, that would also work, right? Wouldn't it? So 4 plus 1/2 I would be somewhere here. Now if I connected these dots, what kind of shape do you think I would be getting? A polygon? No, you must use a smooth curve, not like that, right? So you kind of need to go smooth like this, maybe, right? Okay, what does that look like? Let's find out. That's actually a hyperbola. So our equation is xy equals 2, z is equal to x plus yi, and this is our locus or loci or whatever you want to call that. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.